Okay, so this is one of the projects that we talk about in chapter 28, which is just interesting projects. In this case, we're going to use an XY display and a microcontroller to put images on the oscilloscope here. So what we've got is our microcontroller here. It's running off of 5 volts power supply, and then we have our oscilloscope. This is an analog scope in XY mode. That means that the channel A sets the X direction, and right now it's about half a volt per division, and channel B is the Y direction. So I turn off channel 1, and we don't have anything in the X direction. I turn off channel 2, we don't have anything in the Y direction. And what we're doing is we're outputting voltages, and the voltages we're outputting are the dots. So we start out putting out 0, 0 volts. I've got that sort of in the lower left-hand corner. And then we output the maximum voltage at this point. So the DAC that we're using puts out 2.048 volts. It's maximum voltage. So we don't change the X, but we change the Y. And then we change the Y back to 0. We go over, and that's why we have a set of connected dots. So what's our hardware? Hardware is our microcontroller, and we need 2 DACs. We only have one in the microcontroller, so we're using an external DAC. Since our microcontroller likes to talk to things through a serial connection, we're using an MCP 4802. That is a dual serial SPI, serial peripheral interface DAC, and we've got a set of points in memory, and we're outputting them sequentially. They go to the scope. You can see that as we jump from one point to another, we get a bit of a trace. We can use a digital scope. It doesn't work as well, but it's usable, and we'll show that towards the end of this demonstration. So we've got the set of points. To create the set of points, I'm actually using an Excel spreadsheet because Excel will graph a set of XY points for you. So I get the points in Excel, and then I dump them in a text format and put them in my code. So here's the Learning the Art of Electronics logo. I can press and switch to the next image. That happens to be a cube. 1, 2, 3, 4, 5, 6, 7 points, because I don't have the back one shown because it's a solid cube. And I can even show the dog horse. This is inside the book. So this uses the hardware in figure 28.10. The DAC that we would be using is an 8-pin device. It has an internal reference of 2.048 volts, so that's the largest output we can get. It comes in 8, 10, or 12-bit versions. They're all identical, and they did something smart, which is you send a 16-bit value through the SPI, and the lower 4 bits are used for the 12-bit version. We ignore the lowest 2 bits for the 10-bit version, and we ignore the lowest 4 bits for the 8-bit version. And what that means is it doesn't really make a difference which version we use. 256 by 256 is more than adequate. If you wanted to use 4096, you could. I don't think you'd see any difference. Now, you'll notice that because we're starting in the lower left-hand corner, because our output goes from 0 to 2 volts, that it always shows something in the left-hand corner. Because the DAC is unipolar, 0 to 2.05 volts or so, we always start in the lower left 0, 0 corner and go to the right. Since these are all approximately the same size, it doesn't make much difference. But the book talks about using a multiplying DAC so that we can get a zoom effect. Now, a multiplying DAC sounds fancy, but all it really is a DAC where instead of using a fixed reference, you put the reference in, and the reference can go from 0 to some maximum value. And what that means is that the output of your DAC goes from 0 to whatever the reference is. So if the reference is 0, you just get 0 out all the time. If the reference is 2 volts, your output goes from 0 to 2 volts max with the largest count. In this case, I think we're using a 10-bit DAC, so that means a count of 1023 gets you 2 volts. And if you put a reference of 3.3 volts, which is the one we're going to be using in the next demonstration, you go 0 to 3.3 volts. That's kind of neat because it allows us to animate what we're doing. And the way we do that is we use the DAC inside the microcontroller, a third DAC, to set the reference voltage. Now in this case we have a 14-pin part. This is a 4902. It's very similar to 4802 except that it has an external reference. There's separate references for the 2 DACs in there, so you end up with a larger package. And what we're doing is we are setting the reference from 0 to its maximum output of the DAC inside the microcontroller, and the maximum output is 3.3 volts. So that gives us this real nice animation effect. The only problem with is because it goes from 0 to 3.3, it seems to grow out of the lower left corner. We can look at each of the demos. Here's the cube, it grows out of the lower left-hand corner. And another thing we can do, it doesn't necessarily require the multiplying DAC, is we can animate by putting up several different but similar images. So here, this is the image that's shown in 28N.14. And we are showing you 3 different images that seem to show I guess it's a dog, where the book isn't quite sure of the picture that's in there. This one's slightly different. It's animated, and we're changing the multiplier a little bit. We changed the multiplier by about 10%, so it looks like the dog is getting bigger and smaller for each animation. It makes the animation more real. Now, one problem is you might not like everything coming out of the lower left corner. You might think, well, I'd like it to zoom out of the center of the screen, and that's possible, but it requires some extra circuitry. We've got the circuitry in 28N.11, and it's pretty cool. It's a great application of analog computing. I urge you to figure out how it works using the principles that we talked about in the first op-amp example. And what it does is that it sets the 0 point at 1/2 the reference. So let's take a look at how that works. I have to move the connections here because right now I'm looking at the DAC output, and I'm going to move these over to after the circuitry that adjusts the offset. So we're now offsetting the output of the DAC by 1/2 the reference. So that means that when we output 0 out of the dual DAC, we should be centered. And it doesn't really look a whole lot different with the static images, but you can see that now we grow from the center. As the reference increases, we change the offset so that it always keeps the 0 point in the center, and it's as though we had a bipolar DAC, which we don't. We have a unipolar DAC. Same thing with the cube. And this kind of looks more like what you expect a zoom to look like, particularly if you've ever watched old Outer Limits. And finally, here's our animation. Looks sort of the same, but we're centered. So this is kind of fun. Once you have the code, it's pretty easy to create your own animation. The book has links to the spreadsheet that I used to create these, so you can put in your own XY points, see how they look with the XY plot in Excel, so you can make sure they're correct, and then you just copy that into the code and call it, and there's examples for you to try. So this is a neat circuit, but in particular, the offset circuit is quite clever. It's an analog computation. It only requires one dual op-amp. And why don't we zoom in and look at some of these again. Now, one thing I should mention is that we've put an RC network on the output of the DAC. If we didn't do that, we would move very quickly between the dots and you wouldn't see the lines between them. We've got 2.2K times 0.01 microfarads. Let's see what that is. And that's 22 microseconds. And what that does is it slows down the output so that you actually see the beam as it traverses. If we didn't have that, it would look like just a series of dots. So let's zoom in. Okay, so here is the output of the circuit with the offset circuitry in, and you can see we're centered. There's our Learning the Art of Electronics logo, our cube, and our fixed dog. You'll notice they're fairly small because I've set this up to work just like the 4802, the version that is the internal 2.048 reference. So we only get about a maximum of 2 volts in each direction. If we go to the multiplying DAC where we're going to the full 3 volts, we pretty much fill the screen. Once again, we're set for 0.5 volts per division. So that's our animated Learning the Art of Electronics logo. Here's our animated cube zooming from the center. And there's our dog running along. And the slight change we use in zoom gives it a little more animation, and I'm not going to say it makes it look real, but it makes it look more fun. And let's go back and look at the unoffset version. And here we are. This is the version that is unoffset, so it grows out of the lower left-hand corner. Not a big deal for the static non-zooming versions because you can always adjust the position of the XY display. But a very different look when we zoom. It's no longer zooming from the center, it's zooming from the lower left. You may like that better. Here's our cube. And then finally, our dog really doesn't look much different. Mostly because we're not doing a lot of zooming here. If you'd like to play with this, I urge you to. The circuit's pretty simple. It's figure 28N.11 if you want the complex version that uses the multiplying DAC and the offset. If you want to do just the simple version that essentially does these images, you can use the version that's in 28N10. This is our XY display displayed on a digital scope, and it works surprisingly well. And here we go. We're going to increase the zoom. Up to the maximum zoom, which is about a 3.3 volt vertical and horizontal maximum value. And it works pretty well, even on our digital scope.